Okay, now to measure MAE through Thiel's U for moving average models, we have to first set up the moving average forecast. So let's go down here, and I have the actual data already set up. So the first MA we can compute when you have MA3 and MA8. So we have to leave the first 8 weeks free. So the first MA8 that we can compute is for week 27, and to stay consistent we leave the first 8 weeks free and start the average for the 3 week. Okay, so it'll be like that for the MA3 model. So we have MA3 model here and MA8 model over there. So now we copy. Okay, so now we have the forecast. So now we can set up the error measures. So MAE. Okay, so now we take the actuals starting from 27. Okay, and then comma. Okay, and then RMSE will be that, and MAPE will be that, MASE will be okay. So now the actual value and the forecast we're considering for MA3, okay, they're okay, but the random walk forecast for weeks 26 for week 27 to 62 will be week 26 to 31. Let's go to the original data. So week 26 through week 61. So that will give us the MASE, and Thiel's U will be the same thing, except for MASE it will be Thiel's U, like that. Okay. Now we need to repeat this for MA8. Now we can examine the table that we have prepared. So the exponential smoothing, the best alpha is here, and you see that this is the best alpha is no better than the random walk model in this case, and the moving average methods 3 and 8 are much worse. So our conclusion here would be to stick with random walk model for this, unless we can find a different methodology completely, not exponential smoothing, not moving average, maybe something else that will outperform random walk. Okay, a couple of final comments about this model. Suppose we want to compare the error measures, okay, of these 5 error measures for the first 26 estimation rows versus the same 5 measures for the holdout rows under the different alpha values. Okay, so suppose we want alpha, okay, equal to 0.2, 0.5 and 0.728. Okay, and we want RMSE, so we have that already computed for the sample data 26. So that's RMSE, MAE, MAPE, then MASE, and right below that is Thiel's U. Okay, so now let's now run the data table here. So we will populate this table with these 5 error measures for the 3 different alpha conditions. Now alpha is in a row, so it's the row input cell, and B4 is where alpha needs to go, and we have the error measures here. Okay, and let's me put MAPE as percentage. Okay, and let's hide this using whiteout. Okay, so these are the 5 error measures for the estimation rows 1 to 26. The same 5 measures for rows 27 to 62 for the exponential smoothing. So let's leave out the MA. So here we want these values to be represented column wise. Okay, so these are alphas, each alpha is in a row, so we can display those here using the transpose function. So first we need to make sure that the transpose will have the same size. So we'll have, instead of 3 rows, we should have 3 columns. Instead of 5 columns, we have 5 rows. So 3 columns and 5 rows. Highlight that and then type the function transpose. Okay, and highlight what needs to be transposed. Now close bracket, but don't press enter. Now, to make this work as an array function, you have to depress the control and shift key. Keep those 2 keys depressed. Don't let them go, and then press enter. Now you can let them go, and now you see everything is displayed here the proper way. Now we can compare, okay, the estimation rows with the holdout rows. As you can see, the MAPE and MAE for the holdout rows are significantly larger than the estimation rows, because in estimation rows the data they play a role in figuring out the best fit. So you can force the best fit, but the best fit for that data, will it be best fit for a data that was not used in developing the model? That's where the robustness of the model is. Okay. Now in the next table in the textbook, they talk about the results that we have obtained here does not change a whole lot when we use, instead of RMSE, if you used MAE or MAP in our solver, meaning that if you go to solver, so we used D34 RMSE to minimize. Instead of that, if you used, say here, let me demonstrate that. Suppose we use MAE to minimize. See, when we used RMSE, we got 0.728, right? If we change that to MAE and run, and you get 0.66 as the answer. So it will be slightly different. Could be, sometimes it may not be very different at all. So you get a different alpha value if you use MAE as the solver objective. So instead of MAE, for example, if we use MAPE, okay, then what happens? Now you get the same 0.66. So MAE and MAPE, they behave in a similar fashion. Actually, if you change, instead of RMSE, if you change to MSE, you'll see that that behaves very similar to RMSE, meaning that you're going to be back at 0.728. So back at 728. Suppose if you want to use to if you want to minimize, say, MASE, that takes you back to 0.66. So our choice here is between 0.66 and 0.728, and even at 0.626, your suppose if you, instead of here, you 0.2 and 0.5, suppose we use 0.66 in the for the holdout sample, and you see you still get for the holdout sample only 1 for MASE and thiel. So what we have demonstrated from this analysis here is for forecasting future sales for WFJ, exponential smoothing model is going to be no better than random walk. Maybe there is another model that can outperform random walk, but not exponential smoothing.